4.5 billion years ago, a vast cloud of dust and gas collapsed under its own gravity. Heavy elements clumped together in the heat near the young sun, forming the raw materials for the inner solar system. Because these early rocky bodies formed in the same cosmic neighborhood from the exact same primordial disk, physics suggests they should have developed into highly similar worlds. Yet the two planets orbiting closest to our sun defied that expectation, evolving into environments defined by absolute hostility. The closest planet is a heavily scarred, barren rock, locked in an orbit where a single day on its surface lasts longer than its entire year. The second planet is completely obscured by dense, rolling clouds laced with sulfuric acid, concealing a surface hot enough to melt lead. They began with identical building blocks, but as they matured, these two neighbors drifted into two incompatible, hostile outcomes. We start with Mercury. It is the smallest planet in the solar system, orbiting roughly 36 million miles from the Sun. The defining feature of Mercury's current state is what it lacks. It has virtually zero atmosphere, only a faint exosphere of atoms blasted off its surface by the solar wind. Without a blanket of gas to burn up incoming debris, Mercury's surface is completely unprotected. Billions of years of cosmic impacts have left it heavily cratered and scarred. This split-screen infographic shows the immediate temperature consequences of that missing atmosphere. The day side, exposed to the sun, bakes at 800 degrees Fahrenheit. Without air to trap that heat, the night side drops to minus 300 degrees. Those minus 300-degree temperatures allow for a surprising anomaly. As this cross-section of a polar crater maps the angle of incoming sunlight, you can see the light bypasses the deep crater floors. This creates permanent cold traps, allowing water ice to survive on the planet closest to the sun. Compounding these temperature extremes is Mercury's orbital maintenance. While it races around the sun in just 88 days, it spins on its own axis at an incredibly slow pace. Because of this sluggish rotation, a single solar day on Mercury, the time it takes for the sun to rise, set, and rise again, takes 176 Earth days. Mercury's current state is a direct result of its proximity to the sun. It is a rocky world stripped of its protective layers by the raw power of its host star. Moving outward, we find Venus. In terms of size and gravity, it is Earth's physical twin, possessing nearly the exact same dimensions as our home planet. The critical divergence between Venus and Earth lies in the air. Venus is entirely encased in a thick, dense atmosphere, made almost entirely of carbon dioxide. This cross-section of Venus illustrates the mechanism known as the runaway greenhouse effect. Solar radiation enters the atmosphere and strikes the surface, but the dense layer of carbon dioxide clouds prevents the resulting heat from escaping back into space. The heat continues to compound. As the diagram updates, the surface temperature pushes past 860 degrees Fahrenheit, making Venus hotter than Mercury. That massive volume of gas also creates a secondary threat. The atmospheric pressure at the surface is more than 90 times greater than on Earth, a weight that destroys modern spacecraft within minutes of landing. Even its movement is an anomaly. Venus rotates on its axis backward compared to most planets in the solar system, and it spins so slowly that its day outlasts its year. Early in its history, Venus may have harbored liquid water oceans. Over time, rising solar temperatures likely boiled those oceans away, releasing water vapor that triggered the runaway greenhouse cascade. Venus now stands as an extreme cautionary example, a planet suffocated and sterilized by its own atmosphere. Placed side by side, Mercury and Venus highlight the different paths of planetary evolution. Both coalesced from the same heavy elements in the inner solar disk, yet one was blasted bare, leaving a silent, freezing rock, while the other became hyper-insulated, boiling itself in a toxic pressure cooker. This orbital map shows the placement of the terrestrial planets, with Earth situated between the airless void of Mercury and the toxic crush of Venus. Studying these dead worlds is a form of planetary forensics. The data we collect helps us map the thermal and atmospheric thresholds that dictate how a rocky planet evolves over billions of years. By deciphering the mechanics that doomed Mercury and Venus, we gain the context needed to decode Earth's past and understand exactly what keeps our own atmosphere in balance. The mechanics of the inner solar system serve as the primary scientific blueprint we use to evaluate the thousands of rocky exoplanets orbiting distant stars. Every chemical signature identified and every crater measured provides new data points for understanding our location in the galaxy. Join us for the next chapter. Subscribe to American Education Tech, turn on notifications, and don't miss Part 3, Mercury and Venus.